In any case, in this decay, strangeness is broken, right? So, strangeness is broken. To describe these transitions, and also knowing that we need to have Lorentz invariance, so we have here current, which is muon current. We need to introduce another current, which transforms K to vacuum or K to pi. And for this we introduce strange current. Which cares, this operator cares, non-zero strangeness, this new quantum number we have introduced. And because of this, you have violation of strangeness. So if you would introduce current which doesn't break the strangeness, then in these interactions or this transition strangeness should be conserved. Okay? So then the Hamiltonian, which is responsible for these decays, can be written immediately as G, and let me put here S, square root of 2, G muon, or actually since we have here also leptonic current, let me write this in general. I would put here L mu, where L is E or mu, multiplied by strange current. This is what we have introduced. And now the index is, so it's better to put S and then mu indexes here, plus Hermitian conjugate. So, this is analogy to what we did before, right, for all other decays. And this is first, again, what we are doing. First try to use what we have already learned. And then check if it works or not. So now, what is this coupling GS? We introduced new, again, for fermionic coupling, or this coupling in front of current times current Hamiltonian, which again has dimension 1 over the mass squared. GS can be found from decay rate. Decay rate, and you can compare decay rate of K meson into muon and neutrino with similar decay of pi. So leptonic pair part is the same in both cases, and the ratio of these decay rates is given by GS squared, which enters K decays, over G Fermi squared, which appears, or let me write, or you can write G pi, right? But it was established that G pi is approximately G Fermi. So the same for fermionic coupling. Multiplied by some kinematical factors. Which are because of difference of masses, because here we have K meson, which is 3 times heavier than muon, and here we have pi, which is slightly heavier, so you have different phase spaces, and therefore you have different kinematic factors, which of course it's easy to compute, and that was computed. And so, measuring the rates of these two, knowing what is this, you can find what is this GS. So, can you guess what is this GS? Well, let me write GS over G pi or GF squared. Can you guess what is this? Remember, in all our previous studies, we had G Fermi or G beta decay, what is in the beta decay, approximately G, what is in the muon decay, approximately what is G pi. So what happens, I told you kind of universality, right? So you saw universality, the coupling was the same in all these parts of Hamiltonian. I should say that we are kind of building up parts of the Hamiltonian. Eventually, total Hamiltonian is sum of these parts which are responsible for beta decay, for muon decay, for pi decay. So we need to sum up eventually all this. Because energy is additive quantum number. So, any guess?
Maybe close, but not too much, like few orders, because the lifetime of K meson and pi.
A few orders. I'm asking about more precise, a few orders. So,
1, close to 1.
What was surprising? That was not 1, but point approximately 0.5. And I should say that this is extremely important fact, which eventually led to introduction of mixing of quarks, or a mixing of fermions in general. Just simple measurement. Again, I want you to understand where all our notions come from. So now I will trace how mixing appears in the theory. So here everything was fine, and it was kind of universality, but this is something new, again strange, right? So you have strange current and something strange is here. So, to account this difference, mixing angle has been introduced, which has the name Khabib angle. And in fact, this angle already appears in the papers by Gell-Mann and Levy. And also Sakata. So things are kind of trivial, right? So you can write general form of the Hamiltonian as G Fermi square root of 2, then leptonic current, as we have written before, multiply it, and now I'm joining currents with strangeness and without strangeness using this angle. So in the following way, I'm writing cosine theta c theta Khabib, then the current, which is responsible for pi decay, plus sine theta Khabib, and current with strangeness. And so sine square theta Khabib should be, this is 0.05. Just a reparameterization, right? I've just joined two currents, and then I satisfy this ratio. Okay? Then effective coupling, which is responsible for K decay, is this G Fermi multiplied by sine theta, right? Actually was later established with preciser measurements of couplings is that G mu square equals G pi square plus GS square. So the biggest one slightly bigger, this G mu, but difference from pi is just cosine square theta, which is cosine theta, which is very close to 1, right? It's 0.95 square 197 actually. Okay, this also has been established, and in fact our parameterization corresponds to the following. It is kind of maybe a little bit confusing. We still call this Fermi coupling constant, this is Fermi coupling constant multiplied by cosine theta Kabiba, and this is Fermi coupling constant multiplied by sine theta Kabiba, and sine theta Kabiba is approximately 0.22. It's just square root of this 0.05. So we refer to this as mixing of currents. So we have combination of two currents which interact with electronic current. Later, when we will introduce quarks, we will see that this mixing of currents corresponds to mixing of quarks. Just remember this. For time being, this is how Hamiltonian has been parameterized. Hamiltonian, which describes both non-strange current and strange current. Strange current has suppression. You see, studies of K-meson decays led us to introduction of a mixing of currents. Then you will see that that actually has very deep sense eventually. But this is how this mixing first appeared. So it's a mixing of currents. I told already that K-meson is a very important particle, and we will study later that K-meson system studies of K-meson decays actually led to introduction of parity violation. Actually, it was first manifestation of parity violation. So the case of K-mesons into 2 pions and 3 pions, essentially studies of these decays led to conclusion that parity is violated, that is asymmetry between left and right in the nature. And that was actually parameterized in these V minus A structures. I already have written correct structure, Lorentz structures of currents, but that came after discovery of parity violation. Not only this, from K, studies of, again, K decays, CP violation has been discovered. Again, we will discuss this in the last part of the course. So to say, you see, the studies of a single particle led to so many things, mixing, introduction of mixing, and parity violation, and CP violation. Questions? So you need to understand how this our knowledge is actually emerges from experimental observations and wish observations. So then you would be convinced that this is the right way to explain things. Yeah.
The angle, is it like another free parameter for the experiment, to fit experiment, or it's on?
Yeah, it's a fit. You see, here it appears as a fit experiment. And you see, we are still struggling to understand. There is no theory which tells you what is this parameter is. So even in the standard model, it appears as a fit parameter, as a parameter. So that is the same problem of flavor physics, which I mentioned already. We don't know the masses of particles, quarks, and leptons, why they are as we observe them, and we don't know how this mixing, what is the theory behind this mixing. So again, we know how to produce this mixing. We can say that, okay, mixing because of some Yukawa couplings, but then we don't know what are these why these Yukawa couplings are such that they produce this mixing. Maybe you will solve this problem. Of course, there's a lot of suggestions and the theories, if you want, of mixing, of quark mixing and lepton mixing. But nothing is confirmed. If you like this or not, so that's the situation. Try to explain. I mean, certainly that will be great, because to have. So it may happen that we actually need to really to wait when string theory will eventually produce something which can be tested. In principle, mixing is, from the string theory point of view, is in multi-dimensional space is overlap of some functions, and then you need to compute this overlap. This is how string people tell us how to compute Yukawa couplings. It might happen that we still can find some theory or the way to explain at least ratios of Yukawa couplings still being in the field theory framework, introducing some symmetries, as usually. This is what we are doing. More questions? Well, everything is simple. It's just simple. This is observational fact. But then it leads to introduction of mixing. We observe these decays, we measure the rates of the decays, and so, again, this is again some assumption, so you don't like assumptions. So this is how science actually develops, right? So, yeah. Now, that was nice in the early days, because there were some assumptions, but then they were tested and led to some predictions. However, nowadays, theoreticians are working, and the number of assumptions is much, much more than the number of parameters you want to explain, and there's no predictive power. So, in these days, if you open theoretical papers, there are 10 assumptions to explain one parameter, 2 parameters, which is, this is where we are. More questions? I want to show you today the slides, actually, if you have enough time. I'll try to do this. So all these discoveries, which we have discussed before, were done in cosmic rays. Now we are switching to accelerator era. Of course, these are not the only discoveries. So I just again pick up the most important. Like you see, this K meson is very important. Pi discovery is extremely important. Muon discovery is extremely important. But of course, there were discoveries of many other particles in cosmic rays. Accelerators. I think in one way or another you know something about this, but I will just do this in more systematic way, because I will then use some material which I will present now, and you will have exercises, so that that's why this introductory part is needed. So we accelerate particles, charged particles, using electric field, right? Magnetic field doesn't accelerate particles, so don't be confused. Although when you are listening some talks about accelerators, people always think magnetic field, the cost is of the magnetic field, the biggest amount of money should be are spent on these magnets which actually produce magnetic field. However, magnetic field just turn the trajectories of particles, but do not accelerate. Don't confuse. So if you have electric field, you have the force, which is given by electric charge, and the strength of electric field. And strength of electric field is given by gradient of potential. So if you have potential which increases from V1 to V2, then charged particle which passes through this gradient of the potentials get the energy delta E particle, which is charge delta V. What we want continuously, we want to get particles accelerated to higher and higher energies. So we started with very low energy accelerators. But then, so we tested if some new particles appear or not. If not, or if something appeared, okay, fine, we have discovery, but then we go to higher energy, assuming that, some new particles exist with bigger and bigger mass, and to produce particles with bigger and bigger mass, you need to have higher and higher energy, right? So, unfortunately, there's a limit to which you can accelerate particles, and limit of the gradient. So, if gradient dv over dx is bigger than 10 MeVs over meter, then you have discharges. Well, that's a problem. Even if you have some cavity which is with very, very small pressure, even if you have almost ideal vacuum, still you have discharges because some particles are emitted from the surface. And that is already enough at very high electric tension to have discharges. So the idea is to use small enough delta V, but many times. So that delta V total is n multiplied by delta V. So that's small enough, but we use it many times. There are two main realizations of this. One is to have really many different parts in our device with delta V. And this is realized in linear accelerators. Another realization is to use the same delta V many times. And this is realized in cyclic accelerators. When particle moves around the circle, and you have some region with delta V, when you have this different gradient of the potentials, and then your particle passes through this region many times. So there are these two different realizations, which I will shortly describe. Linear accelerators and abbreviation is LINA. So here different delta V are used, and many of them. The scheme of linear accelerator, and who knows what our linear accelerators look actually studied? How many of you know how linear accelerator works? Nobody.
Usually they use electrons.
Why? Or you can accelerate any charged particle. Well, you had a nuclear particle, some few particle physics courses, so that. Okay.
Maybe you have many pipes, and in each pipe you accelerate the charge with the electric field higher and higher to arrive to your the energy that you want.
Well, that's clear, but okay, let me draw and then I will ask some more questions. it should be some what we call pipe tube with a very low pressure, evacuated as much as possible, where accelerating particles are moving. Pipe. So particles are injected in some beginning of this pipe, and then acceleration process occurs along this pipe. So how it occurs? The pipe is surrounded by cavities, or sometimes people are calling this clystrons. So let me put it this way. First, to have better drawing, something like this. And so you do not see this, of course. So that's inside the pipe, inside these cavities. And it may be 100 of these cavities. Why? They are usually of the same diameter, but the length slightly changes. So that is what is important. Okay. So let me put this bigger so that. Okay. So these are cavities. I will write here. Oh, sometimes called clystrons. And there are so-called acceleration gaps. So let me also write electric scheme. So this cavity is connected to this cavity is connected to this one, and so it's kind of not each one after another, but alternating. And here we have alternative voltage. So it's usually like this, right? So here apply. So that this cavity has the same voltage as this one, this and this one, etc. And this alternative voltage has radio frequency. This is important, so let me put here radio frequency. Which is megahertz. Very quickly. Now, how acceleration occurs? Suppose we have the flux of electrons. And electrons enter this cavity. And voltage is such that that has minus sign and that has a plus sign. When electron appears in this gap, it will accelerate. Okay? Now, what happens is, so it's minus, that's plus, etc. So when this electron accelerated in this gap appears in this gap, what will happen? If you would have constant electric tension, then that would decelerate. Okay? So how to organize further acceleration? You need to change polarity, right? So that when this electron reaches the second gap, this becomes positive and this is negative. So and the trick is the following. While electron is moving inside the cavity, you change the potential. So I'm discussing this in a more simple way, just saying like this, but in practice it's a sign type of thing. but just for explanation, better explanation. Okay? So, you have polarity plus minus when electron is here. While it is moving inside the cavity, you change polarity. Do I have then the acceleration of electron when I change polarity? So it was plus, then I change it, it becomes minus. So what happens with electron when it moves inside the cavity? You understand what I'm saying? So
It's accelerator.
So what will happen? What happens with electron when it is moving inside and I'm changing electric tension? I switch the sign. What will happen with electron?
Nothing. Nothing.
Why?
Because we are in a cavity which shields it from.
Yeah, you probably know this. Not shields. The point is that what matters is difference of the potential. And if I change potential along all the, so it's kind of, if I change the polarity or sign, so all this cavity is just metallic. It will change the sign of the potential. So the potential in each part of this cavity is the same. I just change simultaneously. And therefore, electron will not feel this, because acceleration occurs when you have gradient of the potential. So this is the trick, right? It's a nice invention, right? When electron moves here, you switch polarity, and so when electron arrives here, that will be already negative, and that will be positive. So again, electron is accelerating here, and this process is continuing. So you are cheating electron. So while he is moving inside the cavity, you switch the polarity, and then in the next gap, it again feels from minus to plus, and therefore it accelerates. So the trick is to change polarity while electron is moving inside the gap. One can present the process in the following way. If this is time or distance, you can treat this in different ways. So you have gaps. So these are gaps. And the electric tension is such that it changes in this way. So while electron is inside the gap, it feels always the same change of the potential increase. This is V. And then the energy, so let me put this, the gaps are, these are the gaps. So this is V. And then the energy changes in the following way. It increases here, then it's constant, then it increases again, then it's constant. With inside the cavities, and it increases again. So this is the change of the energy of the particle. You can immediately figure out one important thing. Of course, you cannot accelerate in this way continuous flux of the electrons, right? Because for time being, I'm just following one electron. But suppose you have another electron which is kind of coming later. Then he will be in the wrong phase, right? And you will not have accelerator. So you should inject your particles in right time to have this process. So this is why acceleration occurs in bunches of particles. So of course you have not one electron, and so what is the bunch? Bunch is kind of volume. small one filled by particles. So you need to create these bunches. And the size can be 1 centimeter, few centimeters. At LHC is 7.5 centimeters, so the length of the bunch where you have particles. I will give parameters of LHC later. And so you inject particles in bunches, small one, in right time. And then all these bunches accelerate. Now I said that that one needs to change this polarity with radio frequency. And again, so typically the frequency is say 30 megahertz. So to say this is 10 to the 7 hertz. Oh, 3 to the 7 hertz. And this frequency is not accidental. This is because you need to change polarity while particle is moving inside the cavity. And if the cavity has, say, length 1 meter, 2 meters, so this is typical size of these cavities, then you need to change your polarity with this frequency. So if you take this frequency, then the corresponding lambda, which is c over eta, this is essentially the length of trajectory when particle is moving, right, with velocity of light, and that would be approximately 10 meters. By the way, I mentioned already that the size of the cavities increases, and the size of the cavities increases along the propagation of particle, because first particle is moving with lower velocity, right? Then velocity increases, but you do not change the frequency, and therefore you need to have bigger and bigger size of this cavity to match these things. So it's constant, but the size of cavities increases.
But as it approaches to the speed of light?
Yeah, so then it's more or less the same. So it's in the beginning it changes the size, and then when it's very close to velocity of light, you have essentially the same size.
For example, how long is the biggest linear now existing?
A few kilometers. And these future linear accelerators could have 30 kilometers, something like this.
Should it really be linear, or like those ranges matches to the curvature of the Earth?
Well, even 30 kilometers is not so big, but and no problem, of course, 30 kilometers to have straight. Of course, what is nice about LINAC that particles are moving straight, not turning, and therefore there's no synchrotron energy loss. So that's important. Okay, so the size increases, lengths of cavities increases. So let me give you some examples of linear accelerators, and one of very important linear accelerators which actually produce a number of discoveries is SLAC, Stanford Linear Accelerator in the United States. It has length 2 kilometers. It has 240 cavities, and it accelerates particles, electrons and positrons, up to maximal energy, 30 GeVs. So future linear accelerators, ILC, which is International Linear Collider, is supposed to have something like 500 GeV maximal energy. And in fact, people are discussing to have some colliders which are adjusted to a certain mass of say, Higgs boson in the center of mass to study in details these particles. In fact, linear collider is actually part of practically everything, all the colliders we have now. Even LHC uses linear collider as initial phase of acceleration. So usually what you are doing, you first use some linac, which accelerates particles to some certain energy, say few GeVs. Then from this linac you inject particle into bigger accelerator, synchrotron usually. And like in LHC, you have one synchrotron, then accelerate in this synchrotron, then inject particles even in the bigger ring, which is this 27 kilometer circumference. At SLAC, actually, what they did, they accelerated both electrons and positrons, and did this in the following way. They have two tubes in which they accelerate one E plus and another one E minus, and actually you can use even the same cavities. But then these accelerated particles were injected into ring, which is called storage ring. And so positrons are moving in this direction, electrons are moving in this direction. Here, of course, you have magnetic field. And then you put the detector here, and this setup acts already as collider because you collide two accelerator particles, although they were accelerated by a linear accelerator. Yeah.
The electron and positron will have different phase for sure.
We will have what?
Different phase because.
Well, it doesn't matter. You put in some trajectory. I think they even, in the sense that they have, if you use the same cavities, that they will have some a little bit different phase. But what's the point? You have somewhere you can adjust your point of collision in such a way that they even, you know, it may be not extremely symmetric. But and then in any case, you accelerate not just a single electron, you have bunches, right? So which means that maybe what you collide here, not the bunches which were accelerated together, but one bunch with positrons, which is before bunch with electron in acceleration complex, and then they collide. So let me now explain, to make some comments about cyclic accelerators. Let me delete this. We will discuss discoveries with this SLAC accelerator later. So cyclic accelerators. So we use the same delta V, but many times because we bend trajectory of charged particle, and so we force it to cross the same acceleration cavity. So the simplest one is cyclotron, which was used in the early days of this technique, and that was like this, just two gaps. Accelerating gaps. So this is acceleration. So you inject particle somewhere here, it moves, and there is magnetic field, what is important. Now we have magnetic field. It moves, then it accelerates. And then the next cavity, already it has bigger energy and therefore bigger radius. Then it accelerates again, will have even bigger, then again. You will have something like this, and then at some point you take particles out of acceleration ring. So the radius changes because your particle accelerates, and the main question here is that P, remember, it equals R over energy over the charge times B. So P momentum increases, therefore radius increases, B is constant. And so the radius, Larmor radius increases, and you have this spiral motion inside the accelerator. So one can do modification of the experiment, keeping the same radius, but change B. B should increase in the course of acceleration, so that you again satisfy this equation. So, and this is the idea of synchrotrons.
The formula might be upside down.
Oh yeah, this is what I so that so the radius, right, in this way is B, E, and here is this is so radius is proportional to P, E, and B, right? So that's the way. And therefore, when you increase P and simultaneously increase B, then the radius is the same. Thank you. So you need to increase B in the same way as energy or momentum of particle increases. This is what is called synchronization. So you need to synchronize change of B and acceleration process. Change of B. And usually you have a ring, in this case, again this pipe in which particles are moving, and then you have magnets, and you have some pieces of trajectory in which you have accelerators. Essentially they act as linear accelerators, and the trajectory is actually not the circle, because it's like here the straight ways, and then you turn trajectory in the place where there are magnetic fields. One important thing here is synchrotron radiation, which I want to talk about. So now particle changes the direction and therefore emit light. So that's extremely important process which leads to limitation of for this type of acceleration. So you have trajectory, a particle with mass x is moving, and so it moves with acceleration, and it emits photons, and this is what we call synchrotron radiation. So it moves and it emits photons along the trajectory. The energy loss, dE over dx, is given by 2 third. Let me give some simplified formula. I don't want to give a long formula longer with various parameters. It's just kind of, but it gives correct dependence on parameters. Momentum to the force power, mx to the force power, and then the radius squared. So the energy loss bigger if you have bigger energies and smaller radius. If you want to reduce the energy loss, you need to increase radius. The important dependence here is this mass of the particle to the force power. Remember we discussed radiation energy loss. And in radiation energy loss, dE over dx radiation was inversely proportional to the mass squared. And it was proportional to the energy of the particle, or momentum if you want, or momentum. Let me explain the difference. So this is synchrotron, and this is radiation energy loss. Here, the energy loss occurs in the electric field. Remember, that what happens in electric field. So that the force, which leads to acceleration and therefore radiation, was electric force. Here, this is magnetic field. This is magnetic field which actually leads to bending of the trajectory. And therefore, force acting on the particle has different dependence on the mass. And that leads to this, this difference. So again, let me use kind of classical, essentially, analysis to explain the difference. Let me make another comment. So this is the reason why we cannot accelerate, for instance, electrons to high energies in the same ring. Lab experiment, which was working in the same ring as LHC now, accelerated electrons up to, say, 100 GeVs only. And we could not accelerate more because of this dependence. So you have too big energy loss. So which means that we inject the energy, so we put the energy, but it immediately loses onto this radiation. So at some point, acceleration process essentially stops. So the energy loss becomes equal to energy which you are putting in. You will have exercise to play with this. So for electrons, using the same ring, which means the same radius, we had acceleration up to 100 GeVs, and LHC accelerate particles up to 7 TeVs. See? 70 times bigger. This is because LHC accelerates protons. And the mass of the proton is much bigger than the mass of the electron, and therefore the energy loss is much smaller. So this one, yeah?
Does energy injection happens also in the synchrotron?
Yeah, of course. So I told you that there is this ring, and then in some pieces of this ring, you have essentially Linux or Linux type
Short
of the,
Linux.
yeah, some short Linux, yeah, some accelerating parts of the project.
They should have reached at least a minimum velocity so that the Linux in between the magnetic banding machines can accelerate them in phase.
Yeah, everything is synchronized. I mean that's.
But we always need to have a ground Linux that makes particle from 0 to some.
Yeah. So first it's just usual Linux, and then this synchrotron with magnetic field. So let us consider particle which is moving along this trajectory. The force acting on this particle is given by change of the momentum in the unit of time. So suppose in the unit of time, particle moved along the trajectory, and this is the angle, change of the angle. So in the first moment, particle was moving in this direction, and then it moves in this direction. And this is again the same angle alpha. So that delta P in the unit of time, or delta T, equals P multiplied by alpha. So these are momenta. And the change of the momenta, this one, it is P multiplied by this alpha. And alpha is the angle which actually traces how particle moves along the trajectory. Now what is this alpha? Alpha equals V, velocity of particle, divided by R, right? So in the unit of time, this distance is just V. This is radius. And therefore the angle is given by V over R. Now V, in turn, is P over mx. And therefore alpha equals P mx, the radius. And I insert here into this formula, and so I will get expression for the force. It will be P squared over mx multiplied by R. So this is the force which leads to such a bending of the trajectory. You see what is important, that force is inversely proportional to mx. Remember, in the case of energy loss, the force was just E multiplied by the strength of electric field. And it didn't depend on the mass. So this is origin of one of these powers of the mass. Now, what is acceleration? Acceleration is force divided by the mass. And then we will get the second power as P squared mx squared and the radius. Remember, this is classical consideration, and when we will go from classical to quantum, we usually square characteristics, which we get in this naive classical way. This is what we did also for radiation energy loss. And therefore, A squared is P to the force mx to the force multiplied by the radius squared. And this is precisely the parameter which was staying in the formula which I have written before. So again, the difference from usual radiation energy loss is that the force now depends on the mass of the particle. Questions? And so that is proportion dE over dx.
Is there here any relativistic correction?
Oh yeah. So I don't want even to write this relativistic formula. If you want, I can. I don't want just to.
It's not response for the 4 power. It's just from the quantum mechanics.
Yes, so of course you need to use quantum mechanics, but you will get again the same factors. You know what is kind of, again, it's non-trivial to derive this formula. So starting from the first principles, but you will get up to parameters, some coefficients, you will get the same expression. And the main characteristics are sitting here. So what you need to remember, so these dependencies, functional dependencies, P to the force, the mass of the x to the force power, and this radius square. You can play with this formula and to see what should be set up of your accelerator to get appropriate energy. And of course, if when this energy loss becomes comparable with injection of energy, then acceleration process just stops.
this is the main reason for construct the linear accelerator, only the energy loss, or there is another important reason?
Yeah, so that actually explains all the kind of program or strategy of acceleration experiments, right? So either you are going to bigger and bigger distances, and nowadays people are discussing even something which is more powerful than LHC, to have energy 100 TeV. So LHC will have energy in the center of mass 14. So increase by 1 order of magnitude the energy. But for that, the ring should be at least 100 kilometers, not 27, but 100 kilometers long. So that, or you go to linear accelerators, and it's another, of course, option. But even this becomes very big if you want. So linear accelerators, again, people are discussing like this 500 GeV, so on. And of course, if you want to have high energy electrons, then it's better to go to linear accelerators than to these rings. Okay, the biggest one was a LEP accelerator for electrons and positrons. So using this formula, you can immediately see what you need. Okay, now let me discuss a little bit characteristics of accelerator experiments. And this is important for our discussions of future discoveries. So we had a number of different accelerators which accelerated different particles. So we have E+, E- collider. And we refer to collider usually when we accelerate both particles which actually interact. And so we have two beams facing two beams which collide, and that's what we call collider. And the important colliders were LEP. And then I explained already that SLAC, they also managed to have collisions because they accelerated the plus and minus and then put them into a storage ring, and then at some point these particles collided. Then it was collider E and proton, kind of asymmetric, right? That was in Daisy, Germany. Then it was collider protons and antiprotons in Fermilab, Tevatron. Then LHC collides protons and protons. And of course we had a number of experiments when we collide muons and, muons and nucleon. Let me put this in this way. So muon and nucleon. And neutrino and nucleon collisions. So these are fixed target experiments. So we accelerate muon or manage to get high energy neutrons. However, target is fixed. It stays. So we are not accelerating the second colliding particle. Let me write. Configuration is fixed target experiment. And colliders. Important parameter of the experiments is total energy in the center of mass. It is, let me put total energy. So what is this? Suppose we have two particles which collide. And they have momenta P1 for momenta and P2. So some of these particles can be at rest. Then you have just a mass of this particle and momenta 0. We introduce the following invariant, which is E1 plus E2 squared minus P1 plus P2 squared. So this is Lorentz invariant. And the total energy in the centrum of mass is square root of this invariant. So square root of x is what we call total energy in the centrum of mass system. This is kind of historic way we denote this. So why we call this square root of s, and what is this centrum of mass system? Centrum of mass system is defined as the system when P1 plus P2 are 0. Okay? So if you collide particles with the same mass, like say proton and proton, then you have a really symmetric situation when proton and proton collide, and then laboratory frame is coincides with a centrum of mass frame. The same is for E plus and minus. And if you accelerate particles up to the same momentum. Okay? So if this sum is 0, then square root of s is given by E1 plus E2 according to the definition of s. And this is nothing but total energy, right? So this is total energy. This is total energy available, which you can spend as you want. You can produce some new particles. You just have this scattering. Okay. Now, important thing that using just energy momentum conservation, to produce particle with the mass mx, you need to have square root of s bigger than or equal this mx. So if, and I will discuss this later in more details, if you have square root of s just equal mx, then you produce particle at rest. So you do not spend energy on some kinetic or some other particles accompanying this one. So this is the reason why you need to have more and more energies if you want to produce particles of bigger mass. Another important parameter is luminosity. So we'll discuss more about this kinematics later. If you have some questions. Yeah.
If those two values are really near to each other,
if
those two values, the energy that you produce and the mass of the search particle, the probability is also changing, right? We may produce some other light particles.
Well, if it is bigger, yeah, so then we produce more particles, yeah? Yeah.
But
photons, for instance.
For example, in the search of Higgs boson, people predict that it should be in a certain energy range, but to be sure, maybe we need to go beyond.
Well, it's more complicated because what we produce Higgs boson in collisions of quarks, of fluxes of quarks. So you always can kind of find quarks with in one proton and another in such a way, with such an energy that they are producing just Higgs. It's like a resonance, if you want. But usually we will discuss this. But usually Higgs also produced not as a resonance. So it's produced by, say, what we call gluon fusion or things like that, and therefore usually we have some more particles together with Higgs produced, so there's no issue at this point. However, a particle like Z boson, for instance, we produce it in interaction of electron and positron, so E plus and minus. And in fact, we can have the configuration when square root of S is just the mass of the Z boson, and nothing else is produced. Then we are sitting exactly in resonance, what we call, we are sitting in resonance. And lab was operating in such a regime where they produced Z bosons, essentially at rest.
Z bosons at rest.
Yeah, so they had such an event. Yeah. Now, luminosity is extremely important parameter. This is what people are talking. So if you open these papers on accelerator experiments, it's always a question about luminosity and total energy in the centrum of mass. So luminosity is introduced in such a way that event rate equals sigma multiplied by L, by luminosity. So this is cross-section. And this is what we call luminosity, that's L. And this is the rate of events. So of course the bigger L, the bigger rate of events. Dimension of L is 1 over centimeter square second. Now, how we compute this luminosity? And let us consider accelerator, collider. So what we have bunches of particles colliding, bunches, and suppose the area of each bunch is A. Well, actually, the bunch of particles in LHC, so it's like it has the size, the thickness like the hair of a human. So you can imagine something like 6 centimeters long, and the smallness is, like comparable with the size of the hair. And you manage to collide them, so you manage to match it in such a way. So suppose the number of particles in one bunch is n, and another one is n2. So they are colliding. So that's what we want. So we collide on these bunches. So Ni, number of particles in each bunch. And at LHC something like 10 to the 11 particles in a bunch. Suppose n is small is number of bunches. So you have circle with a synchrotron, and then a number of bunches are moving in one direction. So a number of bunches moving in another direction. And then at some points they are colliding. The trajectories cross, and you have these collision experiments. So A again is an area. And it is given by 4 pi, say sigma x and sigma y. And then another important quantity is F. This is number of revolution in a second. Of bunch, of each bunch. So which means that per second the bunch makes, so this moves always with velocity of light, many turns. And so F is number of turns of your bunch. Now to compute luminosity, or first rate, and then we can compute what is luminosity. Let us consider the following. Let us consider that one set of the bunches is at rest. So we can go to the reference frame in which bunches which are moving in this direction actually at rest. So it's target. And others are moving and with velocity v, and then form the flux. So we actually considered already this setup in one of the early lectures, and the rate of events is given by F, the flux of the particles here. So let me put here as 1, and this is 2, multiplied by total number of particles of type 2 in target, and multiplied by cross section. Remember, we derive such a formula, we can look back. So what is this N2 total? It is given by N2, number of particles in each of these bunches, multiplied by N2, number of bunches. Now what is the flux of particles of type 1? It is given by N, number of particles in each bunch, multiplied by N1, number of bunches, multiplied by F, revolution frequency, because the same bunch hits your target many times a second. And then we need to divide by A, the area of each of this bunch. So it's like this, so I have bunch, and this is area. Okay, putting things together, so inserting here and inserting F1 here, we will get the rate. Now we can get already. I can divide this by sigma. So that's what we are computing. Actually, this is what is luminosity, and so luminosity will be just the product of these two, and I will get for luminosity the following formula: F N1, N2, and big 1, and big 2, 1 over 8. So let me repeat. We introduced luminosity as a parameter in front of sigma. Remember the formula, which I have deleted already. So actually the luminosity is given by the flux F1 and total number of particles 2 in a target. So the product of these two leads to such a formula for the luminosity. Apart from luminosity, we introduce also integral luminosity. The integral luminosity is just given by integral over dt L from 0 to t exposure time. So that if you know what is this L integral, you can immediately find what is the number of events which are produced with a given cross-section. So you can compute cross-section of interactions which you are interested in. For instance, production of Higgs or production of some other particle. And you make exposure. So you run your experiment during certain time, and then you can find immediately the number of events as a cross-section multiplied by L integral luminosity. So the luminosity integral 1 has the same units as 1 over cross-section. Because this n is just number, has no dimension, and therefore integral luminosity should have dimension of inverse cross-section. For cross-section, we use the following units. 1 bar, which is 10 to the minus 24 centimeters squared. And this is typical cross-section of strong interactions. Now, important unit, of course, 1 millibar. And this is 10 to the minus 27. Then 1 picobar. Which is 10 to the minus 36 centimeters. And these are typical cross-sections of weak interactions at energies 1 or 2, several GeVs. And what we are using usually in the searches for new physics is femtobarn. Which is 10 to the minus 39 centimeters. So this is actually the level of our sensitivity to new physics at high energy accelerators.
So just, I want to ask about the formula.
Yeah.
So this formula tells us that if we collide our beams with not with the total area from both beams, if we change the angle.
Yeah. So that's more complicated. So this is simplified formula when you have collisions of two bunches and you do not miss, because of course if you just small shift of the bunch, you will of course lose your luminosity.
Yeah.
Even if there is some angle. Yeah. So that formula is for exactly frontal collision.
So if we change the angle, it will increase the luminosity.
Why?
Because in the formula it's...
Well, this is the angle between what? So suppose you have collisions of this and that type. So this one is moving in this and that one is moving in this. Then effective area will be smaller or much smaller.
You can not change it like...
But this is maximal when you have exactly this collision.
I see. So
you can share this geometry if you want.
But if we
Because in this way, each particle from this bunch collides with each particle with this bunch. In such a configuration, this is not the case, because the particles which are sitting here will collide with just part here, then it will go through.
yeah, I see. Or maybe we can make shift one of the bunch just a little bit above, so it will decrease the area.
Yeah,
in
to
such a way
decrease.
to increase the luminosity.
No, how can you increase?
Yeah, I see.
So again, this formula is derived only for such a configuration. And if I have such a configuration, then the formula should change. It's not like I will decrease A.
I see.
You see?
Okay, yeah.
Okay, so now I understand your question.
Yeah, yeah.
See, the point is that you will have bigger luminosity if you pack the same number of particles in smaller and smaller volume.
Yeah.
So that's what this formula tells.
That's the formula.
Okay. Again, this is valid only for such a configuration. For this one, it will be different formula, and you will get that the luminosity decreases. if you introduce some area.
For the formula for area, we had some sigma x and sigma y.
Yeah.
Those were.
I have somewhere. So usually this is in general this is sigma x and sigma y, and let me tell you what is the radius versus in LHC they are really kind of circles. So this sigma x equals sigma y, and the radius. So this is your bunch, and the radius of bunch in LHC is 1.6 10 to the minus 3 centimeters. So and the length is 7.5 centimeters. This is at LHC. So this is it's like a human hair. That's what I was saying. So this is typical radius. And can you imagine that you need to to collide this? And these particles are moving 27 kilometers, and this really fantastic, right? What they did. They managed to do this. Oh, so I'm finishing now. Unfortunately, then I will start tomorrow the lecture for us, showing these, the slides. And I want to finish today's lecture essentially to saying the following, that we are measuring, according to this formula, the luminosity in inverse femtobarns. So you can look at the papers and you say, okay, we have 10 femtobarns inverse, or inverse femtobarns. So if you have luminosity, let me delete this still. If you have luminosity, integral 1, which is 1 femtobarn inverse, and if the cross section is 10 to the minus 36 centimeters, for instance, square, for example, then the number of events you expect is 10 to the 3 in the course of this exposure. So actually LHC in the second run of the experiment has the luminosity integral 1 around 190 femtobar, inverse femtobar. So this is integral luminosity of LHC. So you can then see that if you have production of some particles with cross section, what is this, 10 to the minus 39, 10 to the minus 40, 10 to the minus 41, then you have about one event during this exposure.
This value is for protons.
For protons, yeah.
And for the, like we also had the cross-section for neutrino experiments.
Yes.
They were not produced from an accelerator, so they do not come in batches. But can we talk about luminosity?
Well, it is not correct, because what we produce is, we produce pions. Neutrinos are mostly produced at high energies in the case of pions and K mesons. So those particles are produced in collisions of protons and as nuclear protons and protons. So if protons are in bunches, then all the rest will also have some bunch structure, yeah?
But we cannot make experiments where we can collide neutrinos or...
Yeah, we are not colliding yet neutrinos. True.
You said that the new search of physics are happening around femtobarn scale. But for example, we know that the...
Oh, now it's 1 over, so since we have kind of 10 to the 2 femtobars.
of the luminosity.
Yeah, so integral luminosity, so the sensitivity is, you can have big exposure time, right? So operation time, say. Okay? So that if you have cross section at minus 41, then you expect about one event during LHC round 2 experiment. So that's what you can say immediately. So once you know cross section, once you know luminosity, integral luminosity, then you can say how many events you expect. Of course, then you need to say, okay, what is the background, and then whole this story with all these complications. You may have, say, one event, but so 100 events of background, and it's hopeless to see this event, to identify it. More questions? Well, actually, LHC works as proton-proton collider. So we accelerate protons. In some respects, it is more interesting to have proton and antiproton. However, to have bigger luminosity, people decided to use proton and proton collisions. Why? Because it is not easy to create big flux of antiprotons. So Tevatron was working with protons and antiprotons. So in Fermilab, Tevatron, they accelerated protons and antiprotons. So the question, what you want to collide, quarks with quarks or quarks with antiquarks. However, at very high energies, number of antiquarks in usual nucleons is big enough. Yeah.
In proton scatterings, are we considering the cross-section of 2 protons or 2 quarks, or the main aim is to...
So what we are doing is the following, and I will discuss this. At high energies, essentially you can consider protons as just free quark, so flux of protons as flux of free quarks. But then you need to have this, the distributions of quarks. So what we are saying is that we are using distribution of quarks in protons, for instance. So which means that that gives you number of quarks of a given type with a given fraction of total energy of proton. So we use this one and consider collision of quarks. Forget about protons. So proton information about protons is in these distribution functions.
So the actual question I would like to ask is when we need to calculate the cross-section between them, we are making basic calculations on QCD, right?
It depends which process you consider. So if you produce some weakly interacting particles like W boson, or so what you are doing is you consider first elementary process, which means, for instance, collision of 2 quarks or annihilation into W boson. But then you integrate over the number of quarks, and QCD enters at this point.
Yes, but the 2-proton interaction here is not some kind of a nuclear or weak
No, it's not nuclear. Yeah, at least for this end, for very high energies, you can neglect all this kind of say binding energies. If energies are much bigger than 1 GeV, it's just fluxes of free quarks. So you have fluxes of protons, but then you can recalculate what is the flux, corresponding flux of quarks, which I mean. Well, in the lowest order, if you consider weak process, well, I'm sorry, we will discuss this a little bit. So you consider just collision of the quarks and then multiply by the number of quarks, by fluxes of the quarks. But of course, sometimes you need to compute also corrections to this, higher order corrections. In some cases, QCD corrections may be important. Well, it depends again on the process. Okay? So tomorrow I will start with